Welcome Stuart, Massimo and other viewers of our image processing and pattern recognition screencast on tracking, our chosen problem area. I'm Adam and today our team featuring Aditya, Prab, Jenny, Utsav, Anthony and Chan Wu will present our algorithm developed to successfully track a human's walking movements. Video tracking is the problem identified, which refers to the problem of following movement targets automatically over a sequence of frames. The dataset walking from the Visual Tracker benchmark on the CV Lab website was chosen as the dataset used to produce an algorithm to detect human moving objects. The dataset contains a sequence of 412 JPEG images, which was converted into an MP4 and features two humans, whose movements were tracked. Our algorithm made use of various techniques, including the Kalman filter, centroid, and the Harris corner detector. Additionally, as a unique human moves, a bounding box is placed around each unique human with an ID assigned to the human as they progressively move through the video. One major problem when trying to track the desired object was occlusion, when the object in focus, a human, is hidden by another object in the frame. A human is blocked by a pole, making it difficult for the algorithm to maintain the same ID on the human object. There were also problems when training the ground truth, with 18% the highest accuracy found during this training stage, which was a support vector machine. The dataset was split up into a training set and a testing set. With the testing set, 40 frames were utilized, while in the training set, the remainder of the frames were used.
So, why tracking? Tracking is an important approach in the field of image processing. Object tracking helps us locate images, moving images over time in different frames. This problem has several issues that need to be addressed today, such as if the object we are tracking goes out of position or out of range from the camera, then it is harder to detect the object again. An inspiration for this project was taken from the pedestrian tracking project in the Georgia Institute of Technology. It demonstrated a tracking system that visually tracked and counted the number of pedestrians crossing a pathway and the direction from which they entered. To understand this topic further, it becomes necessary to investigate the need for tracking. Tracking is used in the field of surveillance, security, and self-driving cars. Helps us locate moving images over time, and can also help secret agencies to locate criminals and stolen vehicles.
One of the techniques we used was a Kalman filter. The Kalman filter is an algorithm or a bunch of mathematical equations that is used to predict a state, using the current measurements but also using the previously predicted estimates. Because it's in a cycle of predicting and correcting those predictions, it's robust and also is simple to use. In our tracking code, we use the Kalman filter to predict where the tracked object's new locations would be.
The next technique we will be discussing is the Harris corner detector. This Harris corner detector is a widely used classifier used in image processing in the form of algorithms to find corners of an image. It is used to detect specific points on an image or a video. The detector works in three main steps to detect features of an image. The first step is to determine which window outputs the greatest variations in intensity. Then, a mathematical formula is applied and a score R is calculated. The third and final step is to apply the score to a threshold to test this and select important corners of an image, which are then marked and selected. This detector helps to find corners of an image where there are certain interferences contributing to city roads, and thus help gain more information about a specific entity, hence making it very important. The image to the left here shows an image of a car, and this image to the right shows how the Harris corner detector is applied to it and identifies the corners.
The next technique that we'll be discussing is the centroid tracking algorithm, or CTA. This algorithm using image processing enables us to detect and track objects through the creation of bounding boxes, centroids, and calculations of distance. This process works in three main steps. Firstly, bounding boxes are produced through an object detector, as CTA assumes that objects are passing in a set of these bounding boxes. Through computation, centroids, or the center of these bounding boxes, can be created. Secondly, the distance between new object centroids and old object centroids are calculated and updated for each frame of the video. The shorter the distance between centroids in each frame, the greater the assumption that the centroids belong to one object. in regards to the greater distance of centroids assumes a new object. Lastly, IDs are created for each object in the frame, where the detector picks up centroids as IDs and tracks. As you can see in the figure above, centroids represent the green circle and the bounding boxes represent the green rectangle around the object. Just to know that this is not actually face recognition, it is just the examination of centroids and the distance between the new centroids and the old centroids.
CanShift detects the object based on its hue color. It can detect the changes in size and location. So this image shows how CanShift works. So it sets the region of interest as a center of the mass. And then in the selected region of the interest, find the largest density data points, then shift the center of mass to the largest density data points. And then based on the new center of the mass, the region of interest will be set again. And then repeating these steps allows the algorithm to track.
The accuracy of the stationary and moving camera algorithms can be determined by summing the number of misses, false positives, mismatches, and dividing the sum by the total number of objects present in all frames. One mismatch in the first code, or the main code, was when a bounding box was drawn around a car. This was overcome using an ACF people detector in the alternative solution, allowing for a more accurate tracking result. When classifying using a support vector machine, area under the ROC curve returns a value of 0.8 for our algorithm, with a value of 1 returning a perfectly classified data set and 0 returning a perfectly inaccurate set. The area under the ROC curve returned a false positive rate of 0.22628 and a true positive rate of 1. According to a journal article from the Journal of Thoracic Oncology entitled Receiver Operating Characteristic Curve in Diagnostic Test Assessment, claims that area under the curve of 0.8 is excellent, with 80% of the frames from the algorithm matching the ground truth which was used for the training. However, when training the ground truth using the support vector machine classifier again, but changing the parameters by changing the kernel to the Gaussian kernel function, it recorded a 0.99 value signifying a perfectly classified data set. However, it may be misleading. The Gaussian kernel function works by transforming the dot point in the Gaussian function of the distance between points in the data space.
Here is a demo of the tracking code running. As you can see in the video player, it is tracking the location of each pedestrian as they are walking with a bounding box and labeling each box with an integer ID. On the right is a second video player playing a black and white binary mask that displays a segmentation between the moving objects and the background. It is important to note that you must download the Computer Vision Toolbox from the add-on manager on MATLAB, otherwise the script will not run. The main function is structured as a function that calls upon its nested functions inside. Firstly, it creates and initializes system objects, tracks, and the next track ID, which will then be incremented for each detected moving object. Then, while each frame in the video is read, it will detect objects in the frame, predict new location of assigned objects, assign newly detected moving objects to a track, update locations on assigned tracks, update unassigned tracks, delete tracks with no detection, create new tracks, and then display the results via bounding boxes and the binary mask. And then it will end the loop when the video runs out of frames to read. As the function name states, this function's purpose is to create the 5 needed system objects to track the motion-based objects. Firstly, it loads the video we want to track onto a reader so that the frames can be read. Secondly, it creates 2 video players, which was shown in the demo. One that plays the video normally with the bounding boxes, and one with a binary mask. Thirdly, it creates the 2 detectors, a foreground detector that distinguishes the objects from the background, and a blob analysis detector that finds groups of pixels that are likely to be the moving object and computes their characteristics. The function to initialize tracks creates an empty array with the fields ID, bbox, Kalman filter, age, total visible count, and consecutive invisible count. The function readFrame simply runs the video reader we created in the setup system objects function and reads each frame in the video. The function to detect objects firstly runs the foreground detector from earlier, frame by frame, and then applies morphological filters. These filters preserve the background and foreground by erosion followed by dilation, and vice versa, and then flood fills the background. It then runs the blob analysis detector from earlier as well. To predict the new locations of existing tracks, it uses the Kalman filter to estimate the new location based on the old locations and then moves the bounding boxes to the center of the new location.
Assign detection to tracks function. The purpose of this function is to, in the current frame which the algorithm is looking at, it will look through the existing tracks and will find a way to minimize the costs. And a cost is essentially negative log likelihood of a detection corresponding to a track. And the function uses Moncrief's algorithm to minimize cost. So essentially, this function returns an m by 2 matrix corresponding indices to the assigned track and detection in 2 columns, and also returns an indices that are not assigned. Alright, so update assigned tracks function purpose is to update each track with a corresponding detection. This calls upon the vision.calmount filter to estimate the corresponding location. And the vision calmount filter is part of the package which we installed using MATLAB. And it also counts the bounding boxes and increases its age while increasing its count as well. And it also sets invisible counts to 0. This function returns updated tracks with corresponding detection and counts. The update unassigned tracks function simply marks each unassigned track as invisible and increments it by adding it by 1, thus updating the list of the overall MATLAB algorithm. So this one essentially just returns an updated track list with its respective count. And the delete lost tracks function purpose is to delete tracks that have been out of the frame for too long. So if someone's walking in a frame and they just leave the frame entirely, does not want to still be there. That's why this function just deletes it to get rid of that number. And this ensures that nothing's being counted. So essentially this function returns the video player which is not displaying the results of the people being tracked. Create new track uses unassigned tracks and converts them into tracks. It assumes that the unassigned detection is beginning of a new track and will give it an ID, age, and etc. So it gives it essentially an ID, BB box, CalMel filter, age, and total visible count. So this gives any unassigned tracks a value and helps the algorithm process what is happening. Other noise detection can also be minimized, but we have not added that into this algorithm for the sake of simplicity. So essentially this returns a potential new track and it adds it to the list. Alright, so the last function in this algorithm is the tracking result. So this is a window that pops up when you run the algorithm. So all this code here is essentially setting up the boundary boxes which surround the people walking in the track. It shows the colors, the RGB as well. It's defined over here.
This alternative code shows how to perform automatic tracking and detection of people in a video from a moving camera, not a stationary camera like the previous code. This is ideal for automotive safety applications in self-driving cars and in security. An auxiliary file, people detector, and global parameters are added to the main function in this alternative code. The auxiliary file relates the pixel location in the image to the size of the bounding box marking the person's location. The people detector allows for tracking of upright people. The ACF bit in the code means that this tracking is done using aggregate channel features. Global parameters are used to simply optimize the tracking performance. These are the global parameters used. No foreground mask is created in this alternative code. This means that only one video with the boundary boxes will play when the code is executed. A second video with a white blob mask will not be displayed. Also, the auxiliary file, scale data file, is loaded in this function. So this is where the scale data file, the auxiliary file previously mentioned, is being loaded. In the track initialization process, 4 new attributes are added, namely color, scores, confidence, and pred position. For display purposes, the color of the tracks is shown using the color attribute. The scores attribute records the classification score from the person detector with the current detection score at the last row. The confidence attribute stores the past maximum and average detection scores with a predefined time window to produce a pair of numbers that represent how confident the system is with the track performed. The pred position attribute predicts the bounding boxes of the next frame. The consecutive invisible count attribute, which was in the first code, is omitted in this moving camera alternative. The process for reading frames is the same as was in the first code. No morphological operation is executed. This means that the images are not processed based on shapes. Instead, the ACF people detector is run within a region of interest to produce detection candidates. Also, as there is no foreground mask, no blob analysis is performed. Multiple bounding boxes surrounding the objects in images are displayed when detecting objects. This is not what is required when detecting people, but is required when detecting objects. When a single pedestrian is to be tracked in a crowded road with multiple cars or cycles, the first solution will not produce effective results. To counter this, non-maximum suppression is used in the second solution. Non-maximum suppression here. With this, only the strongest bounding boxes are displayed, hence people are tracked. In this function, the only difference is that bounding boxes are shifted so that the center is at the location predicted using the pred position attribute. Now, Charlie will delve into the complexities of the remaining alternative code.
So for this function, only the difference is it uses the bbox overhead ratio function. So the cost will be computed based on this method. The overhead ratio is between the predicted bounded box and the detected bounded box. So next function is update assign tracks. So based on the average size of preset 4 boxes, the new bounded box is stored. And updating the tracks age and the visibility is basically same as the main code. So update on assign tracks is set the assign track as invisible and increase the age by 1 and it appends the predicted box to the track. So for this function, so it uses the noisy detections to find the false tracks. So check the maximum detection confidence score. So confidence score means how confident the data is. And find the indices of lost tracks. And then based on that, simply delete the tracks. So create new tracks. For this function, it creates new tracks from unassigned detections and assume that any assigned detection is a new track. So only difference is the presence of score variable to show how accurate the data is. Yeah, this is just a screenshot of alternative code.
In conclusion, both sets of codes, the alternative and the main code that we spoke about, have unique features and vary depending on the circumstances. Code reading can be also improved, but it is a good starting point from our team's base knowledge of where we began with MATLAB. Overall, the team has learned the concept of human tracking and its application in everyday life, and how we can actually apply it in the real world. Some lessons we learned was how to develop in MATLAB, and evaluating and testing various algorithms for human tracking.